thank you for coming down today.
Absolutely.
Having someone like you here to talk to is absolutely essential, because in my mind, like, you were the person I had to sell it to first. I had to prove this idea that this technology would work, and that it would actually benefit the networks and help people and deploy faster. All those benefits. I knew they were there, but I had to talk to someone who knows it and does it to really like talk about how that's gonna help in those scenarios.
Yeah, and I can't blame you, because like when I first heard about it, I was like, well, that sounds cool, but why?
Yeah.
Like, okay, sure, like it's another wireless communication technology. Great. We have microwave. There's 18 bajillion different, wavelengths we can use in microwave. You can use 11, 18, 60, 70, whatever you want. There's various different ways to use them. Why does this matter? And when you came to me and were just like, hey, it's a way that we don't ever have to worry about talking to the FCC. I was like, I'm already sold.
Yeah.
Because it's just like, when you have to go through spectrum, just allocation discussions, it's a headache. It's expensive, because if you don't have that expertise in-house, you have to pay an engineering firm to do that study for you. That's not free.
Right.
Maybe it's a 2-mile link and 11 gig doesn't work because 18 gig doesn't work because it's too far away, and 11 gig, oh, well, there's this one tree that's kind of in the Fresnel zone. It just doesn't kind of get the speed you want. Oh, so what do I do? Oh, I guess I can wait, a year and get a fiber run. Oh, well, I guess I'll just delay this entire, cell site setup. Or you can just use a laser.
Yeah. So yeah, tell me a little bit about the millimeter wave. Can you just walk me through, how the setup of that and things like that, and then we'll discuss the difference in how to set up this technology.
So, millimeter wave. I mean, the last setup I did was didn't have any millimeter wave, but it used CBRS. I want to talk about that for just a quick second instead, because it's actually better and worse in a lot of ways. And CBRS being the one that everybody wants to talk about so often because anybody can use it, because it has generally available GAA licensing. You can just use it. You just have to have somebody who has a certification, put it into a system, and you're done. But even with that, it's like there's a lot of contention. There's interference. There's problems with it. Even in the system we were setting up, it was in a rural environment. We couldn't get 80 megs. And we needed that to even get our full spectrum plan. And we were in, no offense to rural Ohio, but kind of in the middle of nowhere.
Yeah.
And if you're talking about anywhere more populated than a series of cornfields with towns that are 20 minutes apart from each other, you're not going to get the spectrum. And millimeter wave is usually licensed. So it's not even mass usable. It's usually usable by specific companies. And in those scenarios, you're talking about, very short range. Sure, it gets really high speeds because we didn't license this 40 years ago because we didn't think it was useful. But when you're talking higher bands, they go a mile if you're lucky.
Right.
And that's assuming nothing's in the way. There's no hills, there's no trees, there's no nothing. I mean, people think that you can shoot through a couple of trees sometimes, and with CBRS, we assumed we could. And then we found out they were mostly pine trees. And to a non-engineer, the non-RF engineer, you look at that and you say, oh, well, they're different trees, so what? Pine trees have a lot more water, and water is bad because it absorbs the RF, it doesn't go as far.
Right.
So you run into these problems where, like, randomly you'll just think, oh, this technology will work, even if it's, close to near line of sight. Might not work. So the difference here is that, yes, the laser is line of sight only. Obviously, you have to see the other side. But maybe you just have to go a little higher on the tower. And then that allows you to be able to get line of sight. And if you can see each other, it's going to work.
I don't think people really grasp like how overwhelmed the spectrum is, especially in urban areas. And, it seems like, well, yeah, why not just deploy some sort of Wi-Fi, to sort of how you're talking about, depending on who your customer is, it's just Wi-Fi, right? It's all kind of just Wi-Fi. So yeah, I think a lot of people think it's a simple problem, and when you really start to dive into networks, you're like, oh my God, this is a cobweb of architecture, and yeah.
I mean, the problem with a lot of RF stuff, especially with modern network setups, is that everybody wanted to, I mean, this was more of a catchphrase a few years ago, but it still applies now. The big buzzword was densification.
Yeah.
We had to get our cell size smaller. We had to cover less people per node. That's how you get better bandwidth speeds.
Right.
That's how you get that. And then with the fact that everything's smaller, you need more fiber, so then you get more fiber to closer and closer to the end user, but you're still using that millimeter wave for that last jump.
Right.
That's how you get the low latency. That's how you get the high speeds. That's how you get something that's actually scalable. That's great, but that is a lot of work from an RF engineering perspective, because you're trying to make your channel sizes as big as possible everywhere.
Right.
Great. You're going to run into interference if you don't make those cells small enough. So it's a constant back and forth effort of just trying to figure out, oh, well, how do we use this? How do we use that? How do we get all these different systems to play nice together so that we don't step on each other and destroy all of the benefits we're trying to get by densifying the network.
Yep.
So then you have, all these different technologies that are put into cellular, like, self-optimizing networks of SON, and various forms of AI that you put into it to try to, simplify that and get it to work without engineers constantly having to touch it. Kind of works.
Yeah.
So it's like there's all these little headaches you find everywhere, and you put in all this additional technology thinking, maybe we'll have a little bit of cost savings, a little bit less engineering hours. It just kind of pushes the ball down the road a little bit.
Yeah.
So you just basically you're putting in all this cool tech, you're putting in all this fiber, you're putting in all this licensed spectrum, and you're having to fight with it to make sure that you aren't breaking it constantly.
Yeah. Yeah.
And when you have all of that stuff, and then you're like, oh, well, I also need a wireless network over there. Well, maybe I have enough bandwidth, maybe I don't. Maybe the signal reaches from here to there, maybe it doesn't.
Yep.
There's a lot of random gotchas you got that if you need low latency, immediate point-to-point communications, it doesn't really serve all that well, especially in urban environments.
One discussion that we often have is, where do you think that this technology fits in the conversation of last mile and middle mile? Because we sometimes talk to folks and we're like, well, yeah, it's a big pipe, right? So it's perfect for middle mile. But there's also there's a limitation of range. So middle mile sometimes tends to be longer, and is it purely situational based, or is it what do you think?
So if I was recommending to some company, like, what do we want to deploy out for this type of connection? This would be one tool in my toolbox,
Right.
that I would really, really want to have.
Yep.
Because if you're having a scenario where, oh, well, we just need to get from here to there, and that building over there is across the railroad tracks. Well, we can maybe get a VPLS from our local ISP, hope that latency is good enough because it's got to go back through their network and then around. We're also paying a lot of, a few $1,000s a month to keep that link up there with a good SLA. Or you could do something wireless. And with wireless, sure, you can do microwave. We've talked about a few different types of that. We've talked about, a few other ways to do it in general, but with wireless, get out there with your spectrum analyzer. Hope that no one ever sets up anything else similar to it.
Right.
Hope nobody ever sets up just a random, small's non sequitur, but you might find it interesting because it was a problem we ran into. When we were running our wireless network down in Covington, there was a sign. It had a bunch of old school incandescent light bulbs, and they would flash. They would do some form of blinking thing when it came on at night. And you're like, what does this have anything to do with wireless?
Right.
Well, they got a bunch of these little buttons. They looked like about the size of a quarter. And they went in between the light bulb and the socket. And what that did is it just made the bulb flash. So it did it at a standard, frequency. So that all the lights did it at the same time. They didn't have to talk to each other. It was just through basic logic. The problem is that they were really cheaply made, and they sent out mass interference to everybody.
Oh, wow.
So our cellular system was getting constant drop calls starting in the winter about 5:36 p.m.
Oh.
until about midnight in about a 4 or 5 block radius around this place.
Wow.
It took us about a month and a half to find it because it was time sensitive. You had to be there and looking in the right place at the right time. It was seemingly random because some days it just wouldn't turn on, find out that they just weren't in business that day.
Right.
Because they didn't have just they were open 7 days a week thing. They were open certain days and not.
Yeah.
And so it was inconsistent. So when you're running just a microwave link, you have a problem where problems like that can just show up.
That's crazy.
And that's not something that anybody would ever think to look for.
Yeah.
And you're going to have to, the only way to figure out what's going on is to physically go out there with a spectrum analyzer, which those are really cheap, only a few tens of thousands of dollars to get a good one. And you run around and you're going to have to scan the network, scan the areas, and find the problem, and then talk to them and hope they'll actually listen to you and fix it
Yep.
before your stuff will even work. And is this going to happen often? No, but it happens.
Yeah.
And that's assuming everybody else is doing everything right. There's nobody, setting up a microwave link they didn't license. They just threw it up thinking, I'm only going to use it for 2 weeks.
Right.
And it happens to be, 2 doors down from you, and your antenna happens to be, a wide beam width antenna, because you only had to go a short way. All of a sudden, it all breaks, and you don't know why. And it was mission critical, and now your other facility is down. And so there's a lot of those types of headaches that you can get from wireless systems, and that's why a lot of people don't like them.
Yeah.
And yeah, they solve a problem. They're really, really good when they work.
Right.
So you have to make sure that you're picking the right solution for the right scenario. And so, yeah, would I still use microwave? Absolutely. There's still times to use it. Is there times to just wait for fiber to get built? Sure. There's times to use MPLS, VPLS. And there's times to just buckle down and use a wireless fiber style solution through lasers through the Theia system, and it works. It's another solution for when you want something that's stable, reliable, high bandwidth, low latency. It's something to deploy, so know that it's out there and use it when it's appropriate.
Yeah, it's an interesting thing that you're not just looking at the line of sight and interference from other systems, but you're worried about interference from just general urban environments and other extra things.
I mean, it can be almost anything.
Anything.
And that's the thing that really causes problems, is that it can literally be anything.
Yep.
And now in today's world, with everybody having cell phones and everybody having various forms of wireless communication, we've done a lot of work to try to make them not step on each other's toes.
Yep.
But it only takes one bad actor.
Yep.
And it doesn't have to mean they're doing anything wrong. It could just be a failing device.
Let me ask a question. Do you think millimeter waves, so the trend, right, that I often talk about is that the trend is that, right, data usage is growing exponentially. How we use our cell phones and how we stream and how, and now AI and data, all of it is growing. And so, one of the thrusts that I had for creating technology like this is that the infrastructure needs to keep up with it. Do you see millimeter wave being able to keep up with high bandwidth throughputs, getting beyond what their capacity is right now?
The challenge with millimeter wave and just wireless in general is the simple fact that spectral efficiency is improving, but not as fast as it used to. The biggest way we've gotten speed increases is throwing more spectrum at a problem. Because it used to be when we went from 2G to 3G, we went from, or even 1G to 2G, we were sitting there, you know, talking about 5, 10 megahertz, 20 megahertz channels. And we were getting more and more speed out of those constantly because we were going with higher, you know, QAM setups where it would actually, you know, you could use the same amount of spectrum, get more speed out of it. It required better signal quality, but we kept pushing it. We've now gotten to a point where to improve that any further, you have to push the technology to a point where the signal quality has to be perfect. And as such, it's like, okay, yeah, we're going to go from this technology to that technology. Okay, we'll get certain improvements. Sure, we'll get things that go better. It'll be easier to manage. It'll be faster. It'll be lower latency. Awesome. We'll have more profiles to set up. Oh, we're going to use it for, you know, video. We're going to use it for on-demand voice, and we're going to make sure that we only give only the bandwidth we need for that specific deployment. But at the end of the day, we're just trying to be more efficient now with what we're using, and we're not getting more speed out of it unless we're throwing more spectrum at it. And as you kind of alluded to, we have gone through and, well, we've really thrown about as much spectrum out at people as we can. And with our current environment, I mean, we've already gone from what we used to call the big 4 cellular providers to the big 3.
Yep.
And even with that, they're sitting there complaining about how much spectrum they have. They want more because that's how they provide more speed, more consistent connections and whatnot. It's created a lot of consolidation. It's still not enough.
Yep.
So millimeter wave, as we go through and we put more and more demands on our networks, more and more demands on the internet in general, I don't know how it keeps up. But if we have other technologies that can supplement it, we get more fiber to more different businesses, to more homes. We get just more efficient with the data we use in general. Things will improve, things will continue to allow us to continue forward, but there's a lot of cost pressure there. I mean, like I said, you know, when I was working with deploying a WISP in rural areas, why were we doing a WISP in, you know, the 2020s for rural area? They couldn't afford anything better.
Right.
I mean, there were multiple of our customers that were still running 3 meg DSL.
Wow.
And I mean that, like, you can't watch 1080p YouTube on that,
Oh.
let alone a Netflix stream that doesn't look completely pixelated out.
Right.
I mean, when we started deploying that, there were kids that started being able to go and use their PlayStations to go actually play Call of Duty with their friends online,
Right.
because their friends lived inside the local town that had cable. But these rural places, like, they could get cable, but it didn't really work. And there was no incentive to really build that infrastructure to them. So it just ends up being that that's a problem with everybody. Rural is just the one that really shows it the most because it's
Right.
the hardest to justify the cost for businesses.
Right.
But that's the problem everywhere. We have a lot of sunk cost with our infrastructure already. We don't want to keep just building the new hotness every other week. So we've got a problem where we need as many different technologies as possible to solve the problem so that we can go forward and actually deploy the services people want to use and will allow for businesses to really offer what they want to do.
I think you said it perfectly. I mean, this is the Theia system is another tool in the toolbox of networking equipment that can help people get the job done, you know, in rural and urban environments.
I mean, if there's one thing I will say, some of the people I've worked for in the past will complain about is that I'm not as much of an evangelist as they may want me to be. I believe in sales engineering in the sense of I'm not here to sell you something. I'm here to solve your problem. It just so happens to be that the thing I'm selling solves your problem.
Right.
So I could sit here and say, oh yeah, no, this technology XYZ, whatever it is the best thing ever. The second it isn't true or you see a problem with it, my credibility is gone.
Yeah.
So at that point, why would I put my credibility on something when I'm trying to say that this is the bee's knees? When in reality, it's like, no, it's a good technology. It solves certain problems. It doesn't solve others. But as long as we look at things appropriately and solve the problems as they should be, we can actually push forward and, deploy out good technologies, build good networks, solve good problems, make the world a better place.
Yeah. Again, going back to setting up a radio link as compared to, or an RF link as compared to the Theia units.
I never really answered that. You're right.
My rough idea of it, right, is that you have to do your sort of path assessment for RF first and run your calculations on how well that link's going to do and perform. Yep. There's then the install, checking spectrum and licensing. And then there's, of course, the install itself, and then you're running. So.
You say that last part like it's the easy part.
Yeah,
the install. See, because you have to because first and foremost, when you're trying to set up a link, you're assuming that you even know which two towers you want to use. Because like when we were deploying out our WISP, we were sitting there and we just said, well, we have to pick any towers that make sense in, this 2-county space is our launch market. How do we pick the best 2 towers to start this all with? We started with 5 towers to launch, and it's like, okay, well, we have to find 5 towers that make good sense for good coverage to all of our different end user customers. Plus then we have to figure out what connectivity is to each of those towers, plus rent, plus everything else, and figure that all out. And the wireless piece is just one part of it. And that's the thing that really makes it just, when you keep throwing one more thing, it's a lot to manage. Yeah. And yes, then you sit here and you say, okay, I want to do a wireless link. Let's just say I do know what 2 towers I want to go to. I do need it to be wireless because there's no fiber there. There's never going to be fiber there anytime soon. So I sit there and I say, okay, well, I'm going to do an engineering study. So we're going to say, okay, at X height, can I get that height? I don't know, maybe. Sure, we're going to find out. We're going to say, okay, we're just going to guess this height. We're going to shoot between them. Doesn't work. Okay, what happens if we go up 30 feet? Okay, I get the link. It works. Awesome. Tool says it works. Then you have to do a physical check to actually make sure the tool's right, because they're using satellite data and some, clutter data that may or may not be recent, depending on where you're going.
Right.
The quality of the data hopefully is good.
Right.
If it's urban, it's probably decent.
Yeah.
If it's suburban, maybe. If it's rural, it's probably not.
Yep.
Because a lot of that data nowadays is collected by drones, just flying and taking position data. Great. The US is a big place. The world's a big place. You may or may not have good data. So assuming then you have to go do a physical check, make sure does the actual, engineering study make sense? Does it actually work? You look at it, you go, yeah, it looks about right. Okay, cool. Now you have to go talk to the FCC or whoever it is, depending on what type of spectrum you're using, or you're using an engineering firm to do that for you. Awesome. Then once all that's done, you have to go through all the leasing stuff. You don't get to install anything for a while. You then install it, and when you get the hardware, you have to make sure it's configured right. You have to make sure you put on all your licenses and everything right. Hope you don't do anything wrong. Test it before you put it up.
Right.
Then you give it to your installer. They put it up. You pray you got a good installer that actually knew what an azimuth was and how to point an antenna. You find out maybe they did a good job, maybe they didn't. Maybe a cable was damaged in transit, even though they did nothing wrong.
Right.
Now you got to fix it.
Yeah.
Now it looks like it's good. Now you test it. You find out your study was good or not. And congratulations, you have a link now. It's a lot of hurry up and wait.
Yeah.
And when managers say, I'll just do a wireless link, that's great and all, but it takes a lot of steps to get that far. And the more you throw one more thing, now you have to make sure you have a project manager on that whole thing. It can't just be an engineer just running with 2 or 3 items. It's now a whole project, and the project manager has to know what the heck they're doing. It's a lot to manage, and there's so many little things that can go wrong. And sure, can deploying out something like this guy, can it go wrong? Absolutely, it can go wrong. But you don't have to worry about the FCC. You don't have to worry about, all these different items. You just need to make sure you have line of sight. And if you do, great, you're done from the actual engineering study perspective.
Right.
So yeah, you have to make sure there's no trees in the way. And yeah, you can maybe run into issues with that. Maybe the LiDAR data isn't good enough and you don't know that there's actually a tree that grew 10 feet since the last time somebody did something.
Right.
Can that be a problem? Yes. Is it a solvable problem? So yes.
Yep.
But you now only have to worry about those few things, not everything else along with it. So it's easier, it's quicker, and it's less of a headache. And as a guy who then has to deploy it, I'm a lot happier because I don't have to sit there and worry about 20 different things and also delay the whole project 6 months.
So if I understand it correctly, I mean, if hardware is pre-configured by us before you receive it, it's simply a hardware install at that point.
Oh yeah.
Yeah.
And sure, I still have to worry about the installers doing their job right, because that's a problem you will always have, and installers will screw stuff up, like misconnecting a grounding bar and burn all of your equipment through a power surge. But
Yep.
not that that's ever happened to me.
Right.
But no, at the end of the day, you still have to make sure the installers do their job, but there's a lot less that can go wrong.
So, when we install, we use a camera, a visual cue, to allow them to line up to the opposite side. What does that look like in the RF world? Just power meter, RX power are you looking at, or what is it?
So typically, because you can only get a full RF link up when you have both sides up.
Right.
The first one, you're just going about, well, I'm supposed to put it at 237 degrees. Hope that they do that right. And assuming they do that right, awesome. Then you go to the other side and you say, oh, well, it needs to be whatever the opposite of that. I'm not doing the math off the top of my head.
The other way.
But you have to figure out the return path. You figure out the degrees for that. You shoot that back. You power it all up. You find out, oh, well, we're about 5 dB off on the signal. Then you do some tweaks here and there. You turn it slightly. You verify. You dial it in exactly. Because a lot of those beams, if you're getting a decent length, you're talking a degree and a half beam width antenna.
Yep.
So they're pretty tight. Like just the difference of a small movement will mean either the link works or it barely works. So yeah, you're gonna have to dial it in a bit.
So it's all manual.
There are, if you're willing to spend more money,
Okay.
there are systems that have, electrical stepper motors that can actually like manually turn it, or there are
Got it.
beam steering systems.
Okay.
But all of those things are more expensive, more
Right.
cost, and it's more upfront capital for the same end result. So yeah, you can do it the manual way or not, but in general, when you're deploying out a lot of these systems, most people are doing it more manual because it's kind of a set it once and forget it.
Yeah.
And sure, the temperature will change, the towers will shift a little bit. Generally speaking, even the not so great ones have small amounts of beam steering,
Yep.
but they're not like wide band, it's like 5 degrees.
Yep.
So it's like, okay, yeah, if things shift, it'll work. But that was a common problem for a lot of deployments for like 60 gig, because 60 gig, just putting that on a wood pole, the movement of the wood pole due to cars driving by
Yep.
was enough to break links.
Wow.
And even with beam steering, it couldn't really keep it stable for a lot of times. So you needed to either mount to very short poles, or you needed to mount to concrete or steel to keep it stable enough.
Yep.
It's like, those are the types of random things that a lot of people wouldn't naturally think about until you deploy your first one. You realize, oh crap, it doesn't work.
Right.
Why doesn't it work? Oh, that's why.
Yep. Well, it's always a little bit difficult for us to try to describe how this technology works, and so it's a nice way to go to that RF stuff and millimeter wave. And if they understand sort of beam steering there, they can sort of think about an even narrower, tinier laser beam and how critical beam steering is, but also how advantageous it is, because that's all an auto process for the system. So if you don't have to worry about, it's a general point and play That should speed up deployment time.
Well, not just to mention the fact, it's got a whole vision system. It can do a lot of correction that, sure, beam steering can do, but it's built in.
Yep.
It's just part of the kit. It functions. So because of that, it's like it ends up enabling a lot more flexibility, and because of how fast this whole system can, dynamically move things, it allows for you to very quickly and very seamlessly connect this to any reasonably two stationary points and be able to get a link.
Yep.
And get the full 10 gig that you're supposed to get, which isn't always a given with RF systems. Because, we think you'll get about 7.3 gigabits per second on this. You put it up, you get 4 and you'll like it.
Yeah.
And
Right.
it's just like, that's what it is. It's because it's based off of not just the fact that you have a link, it's also the fact of what's the quality of the link.
Right.
Laser, you know this better than I do, kind of works or it doesn't.
That's it.
You have a link or you don't.
Yeah, correct.
So it's like, because of that, it's like, you're going to get the speed you get because you have a laser link.
That's it.
The end.
The end. Yep.
RF can be a lot more fickle.
Yeah.
It depends on, we thought everything was fine, but we didn't realize that the Fresnel zone, which people always just think, I can see the other side with RF. There's this nice thing called the Fresnel zone, which is an area around the beam that kind of balloons out and then balloons back down.
Yep.
And if anything is inside that, congratulations, your signal quality is degraded.
Yep.
Laser, you can see it, the end.
Yeah.
It's a much more intuitive technology from that perspective.
Yep. Do you think there is, we do have some access for PoE ports. Is there an advantage for folks being able to hook up security cameras, or are there other RF devices that they can run with PoE, or, is there an advantage there, you think, or?
In general, if you're deploying out networking equipment and you're putting something up on a pole and it doesn't have PoE, you're doing something wrong.
Sorry, so this is PoE out for additional.
Well, no,
okay, sorry.
That's what I mean. It's
Yep.
like if I'm deploying out a point-to-point link,
Yep.
I'm going to power it through PoE.
Yep.
And so if I'm doing some form of like a 6 gigahertz point-to-point link for cheap on a business, because you can get those for a couple $1,000s, those would be PoE powered generally. So I wouldn't be deploying a PoE switch normally. The fact that this also has that same thing is a benefit in that perspective, because it matches what I would expect from a network deployment perspective.
Right.
Because I can deploy out a Wi-Fi access point off of this. I could deploy out a camera off of this. I could deploy out various forms of sensors, like if I just need to put some form of license plate scanner for security purposes.
Right.
All of those things will work. But the benefit here isn't so much that it's a unique benefit. It's more that it matches what I would expect. It's what I would already be deploying. So it makes me just go, that makes sense. Okay, great.
Right. Well, Kevin, I think this has been a great conversation. Thank you very much.
Well, thank you very much.